Hello everyone. Today in this video we are going to learn ionization energy. Okay, ionization energy, which is a very important topic, and there are many competitive examinations in which the questions comes from this topic. Okay, so what is ionization energy? The ionization energy of an element is defined as the amount of the energy required to remove an electron from the outermost orbit of an isolated gaseous atom. This is a nucleus. Okay, this is an atom. Okay, and if there is electrons in many shells, okay, so you will say the energy required, okay, to remove an electron from the outermost shell is nothing but your ionization energy, or you can say energy required, okay, to remove an electron from the outermost shell is your ionization energy. So whatever energy you will require to remove an electron will give you your ionization energy. Okay, and then that energy, when you calculate in terms of work done, if you calculate in terms of work done, then that is called your ionization potential. Okay, ionization potential. Now we will understand what is ionization potential. If you go by definition, it is when such a definition is written in terms of work done, that is the amount of work done in removing an electron. The property is called ionization potential. The unit of ionization energy is kilojoule per mole. Kilojoule per mole. When the property is written in terms of ionization potential, the units are taken as eV per atom. eV per atom. Okay, in terms of ionization, this is IP, ionization potential. Okay, and that one was your ionization energy. It is calculated in terms of kilojoule per mole, and IP, ionization potential, is calculated in terms of eV per atom. Now an atom can have many ionization energies as the number of electrons it has. Okay, that means if you remove one electron, you will require one amount of energy. If you remove the second electron from the second subset, you will require another amount of energy. So the amount of work done, you can say there are many ionization energies, like ionization energy 1, okay, IE1. Then you have your ionization energy 2, ionization energy 3. That means the number of electrons, the more number of electrons you're removing, the more is the ionization, the amount of ionization energy requirement becomes more. Okay, so the atoms can be easily removed, okay, from the outermost shell. Okay, an atom can have many ionization energies as the number of electrons it has. It is denoted as I1, I2, I3, and so on for first electron, then for second electron and third electron respectively. Okay, the value of the second ionization energy is always greater than the first ionization energy. That means ionization energy 2 is always greater than first ionization energy. These are the steps you have to remember, or you can say these things you have to remember. That is, your second ionization energies is always greater than the first ionization energy, and I3 is greater than I2, and so on. Okay, so the first ionization energy will be less. Why? Because you are removing one electron, then you're removing 2 electrons, then you're removing 3 electrons. So this way the ionization energy it increases from I1 to I2 to I3. So your trend is this: ionization energy of first second is more than first, and third is more than second. So this is your first one. Okay, now the second thing is that the value of the reason for such an increase in the ionization energy from first electron to second and to third. Why? That means you say ionization energy I3 is greater than I2 and is greater than I1. Why it happens? Why? Because see, in an atom, okay, when you are adding an when you are going from, suppose, fluorine, suppose, okay, what happens is that as we move along a period, when we move along a period, what happens along a period in a periodic table? If you see, that means here it is S block, okay, and then alkali metals, then here you have P block elements, and here you have D block elements, D and F block, is it not? So now when we are going along a period, what happens is that you are adding electron, okay, you are adding electron to the same subshell, that means you are adding electron to the same subshell, that means your number of shell is not increasing. Now when you go down the group, shells increases down the group, whereas in a longer period the shells remain same. So you are adding electron to the same subshell. When you are adding electron to the same subshell, so and along with an when you go from here to here, you are not only adding one electron more, you are adding one proton more, so your effective nuclear charge is increasing, is it not? First, when you remove one electron, it becomes positive. Okay, it becomes one positive, it will become carbon positive, or you can say nitrogen plus 1 it will become. Then if you remove another electron from it, then it becomes plus 2. Is it not that the nuclear charge is increasing? So as the nuclear charge increases, as your effective nuclear charge increases across a period, okay, as your effective nuclear charge increases across a period, removal of electron becomes difficult. Removal of electron becomes difficult. Okay, so it becomes difficult. Now I will show you like this, with this one as carbon, nitrogen and fluorine. No, so what happens is that as you add electron, that means first time when you remove one electron, suppose it is nitrogen, okay, you're removing one electron, it becomes plus, positive sign. Okay, you're removing one electron, but protons are same, it is increasing, the number of protons are increasing. Okay, again you're removing another electron, 2 electron, again it becomes N2 plus. Okay, N2 plus if you're removing second electron. So this is your first IE1, and this is your second IE. And thirdly, if you take and then it becomes N3 plus if you remove another electron from here. If you remove, then it becomes N3 plus. So what happens is that as the positive charge is increasing along a period, what if you take about only one, so because you're removing one electron, so one time your energy is gone, the second time you're trying to remove an electron from the same subshell, now it's already electron deficient. Is it not that it will try to pull back its electron, it will not easily remove it, so it will not allow you to remove that electron easily. So that's why your second ionization energy becomes greater, and the third one is even more greater. And this is for particular atoms. Just see, this is for any particular atom. Suppose I have taken the example of nitrogen, so I'm taking only nitrogen. Okay, now what happens if you consider different elements like carbon, nitrogen, oxygen, fluorine? Okay, like this also, when it is going from this side, what happens for this one, carbon, nitrogen and oxygen and fluorine, if you check in this way, along this the radius decreases. Okay, why radius decreases? Because you are adding an electron and proton to the same subshells. So even if their subshell is not changing, no, so if you increase one proton, is it not that it will try to pull, effective nuclear charge will increase, and hence your radius decreases. So if radius decreases, that means your ionization energy will be, again it will be more, because it will be more difficult to remove an electron from the subshell. So along a period, as radius decreases, your ionization energy increases. That means tendency of the electron to lose its electron decreases, and hence to remove an electron you will require more amount of energy. So the variation of ionization energy shows the following trend in a periodic table. I will show you how we are showing the trend in the periodic table. Okay, so this way it increases and this way it decreases. Ionization energy, this is the graph. Okay, you should remember ionization energy decreases down the group, okay, and it increases across a period. Why it increases? Because here the size decreases, because the radius size decreases, size of atom decreases, and hence removal becomes difficult. So it is ionization energy increases across a period and ionization energy decreases down the group. Okay, so here what happens, the size increases, is it not, down the group? As we go down, number of subshell increases, and hence your size increases down the group, so your ionization energy also decreases. So you can say your ionization energy is inversely proportional to size of the atom per ion. So if your size is more, ionization energy will be less, and if your size is less, and hence your ionization energy will be more. Okay, so this is the most important thing. And now we will go for the exceptions. exceptions are very much important. Why? Because from this only your competitive examination comes. So what is the first exception we can predict is that the first ionization energy of group 2 elements is greater than the corresponding elements of the group 3. Why? It is due to the presence of fully filled s orbital in case of group 2 elements. Okay, their outermost electronic configuration is ns2. It is always difficult to pull out an electron from the stable electronic configuration. So what is said that the ionization energy of alkaline earth metal, okay, earth metal is always greater than your group 13 elements, group 13 elements. Now consider this one, your sodium, magnesium, then aluminium, silicon, phosphorus. Your sodium is 11, atomic number is 11, and magnesium is 12, then aluminium is 13, silicon and phosphorus 13, 14, 15, and then you come 16 is your sulfur. Okay, so if we consider this one, what happens is that what we will get that the ionization ionization energy of magnesium, the first ionization energy of magnesium is more than the first ionization of aluminium. Why? Because here see magnesium is 12, no? So if we write magnesium's configuration, it is 1s2, 2s2, 2p, 1 2 3 4 5 6, 2p, 2p6, 3s2, is it not? Okay, and then you have your aluminium is your 13, right? So 1s2, 2s2, 2p6, 3s2, 3p1. So what happens is that in both cases the outermost electron of aluminium is in the p subshell, which is larger in size, and it is only one it is just one in subshell of p contains 6 electrons, so only one electron is there. And here it is 3s, the outermost electron is orbit is 3s, and it is already filled. So it is very difficult to remove an electron from the filled orbital than to remove an electron from unfilled orbital. Okay, go to the B, number B. What is the second you can say what is your second exception is that the first ionization energy of the group 15 element is greater than the corresponding elements of the group 16. That means first ionization energy of group 15 elements is more than ionization energy of group 16. But as we know that as we go down across a period, then that means from 15 to 16 size is decreasing, and hence ionization energy should increase. But what happens in this case? In group 15, okay, group 15, so if you take an example of 15, group 15 is your phosphorus. Here if I take this one only, if we take this trend, sodium, magnesium, aluminium, silicon, phosphorus and sulfur, okay, there is 11, 12, 13, 14, 15 and 16. So if you take phosphorus and if you take sulfur, okay, it is 15. That means your electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p3, and here is your 1s2, 2s2, 2p6, 3s2, 3p3, 4s1. Now see, what happens is that as being the last subshell, that means from where you have to remove the electron, here it is the p orbitals, it is already half filled, it has 3 electrons. So and here it has only 1 electron, and that is also in s subshell, that is the 4th subshell. So to remove an electron from the half filled is more difficult than to remove an electron from the s orbital. So therefore ionization energy of the phosphorus will be more than sulfur. So now, we come to very important question now. This question we will solve. The correct sequence of the first ionization energies of the following element is, okay. So you have your magnesium, aluminium, silicon, phosphorus and sulfur. So aluminium, phosphorus and sulfur. So first comes your sodium. Let me write as the periodic table goes on. Is it not? Magnesium comes in this, this is your 13, this is this is sodium is 11, magnesium is 12, okay, aluminium is your 13, then your phosphorus, that means phosphorus 15 and sulfur is 16, phosphorus 15, sulfur is 16. Now we will check whose ionization energy is more and how we can arrange it. So now whatever we have learned in this, now we will go through this one. Now see, what we learned is that the alkali metal, this sodium comes in a group, it is number 11, that means it comes in group 1, okay, and then your group 2, this is your group 2, this is your group 13, this is 15, and this is 16. So as we know that as we go along a period, that means size decreases, ionization energy should increase. That means sulfur should have the highest ionization energy. But is it so? We know that there is exceptions also. Okay, now so see here, sodium, because it is the alkali metals, and here the last subshell is your S subshell, and it has only one electron in the S subshell. Okay, 3s1. Okay, and it can be easily removed, and hence ionization energy of sodium is lesser than your than the whole one. So that means sodium should be your C. So the your last two trends must be your answer. So now let's check what we can do. Now magnesium again being an alkaline earth metal, and it has fully filled s orbitals. So magnesium energy is also greater than aluminium, that we just we discussed. Because why? Because aluminium has again 3p1 electron in the outermost shell, which can be easily removed other than from magnesium, because magnesium has your magnesium your fully filled orbital. Okay, and now see here, in case of phosphorus and sulfur, now it is lesser than this, so aluminium should be lesser than magnesium. So this my answer should be this one. And another thing I will explain, that between phosphorus and sulfur, phosphorus IE is greater than sulfur. Phosphorus is greater than this IE of sulfur. Why? Because again this one has 3p3, so it's half filled p orbital. So removal of electron becomes more difficult from half p orbital than your 4s orbital of sulfur. So your 10th will be number 4. So this is a very important question, comes in your TGT exams. Okay, so let us know this. So this is your answer. Number 4 is your answer. Now we will go for something, is that atoms and ions having inert gas configuration has the highest ionization energy. That means inert gas, whatever we have group 18 elements, okay, or I can say group 18 elements will have highest IE. IE is highest. Why? Because you have to remove an electron from the fully filled subshell, and it's very difficult. And the second is that the the alkali metals has the lowest. Alkali metals or S1 group 1 elements has your lowest IE, lowest ionization potential, first ionization potential. Okay, and the third is the order of the energy required to remove an electron from the subshell is S greater than P, greater than D, and greater than F. That means from S it is more difficult to remove, then P, then D, then F. Why? Because S is closer to the nucleus, okay, and P is little bit far, and there are Px to Py to Pz. That means these are diffused. So as we go from P to D, the diffusion, the orbital are diffused. So it is easier to remove an electron from the diffused shell rather than from S shell. But exceptions are always there. In order to the closeness of the above written subshells with the nucleus, out of the 4 given subshell, the S subshell is nearest to the nucleus, while the F subshell is the farthest from the nuclei. Alkali metal has the lowest, and the inert gas has the highest along a period. Among all the known elements, helium has your highest IE, and your cesium has your lowest IE. You should remember this. It might come in any examination. IE. Okay. Now, so this comes to the end of ionization energies. Okay, and we can go for next topic. We will go for electron affinity. Thank you so much, and I hope you will understand the ionization energy. And now if you get any questions, you can solve it, and if you have any doubt, please do give a comment, and or else you can just even check my Instagram ID and just send me a message regarding which question you are facing difficulty. Okay.